Broadcast is starting. All right, what do we got here? What do we have here? That's what I'm trying to ask. What do we have here? We have people in the house. Everybody, yeah. Rock your convolutional network, yeah. Okay, hi everybody. Welcome to the live stream today. We are going to build a convolutional neural network, and we are going to build it with just TensorFlow. We are not using Keras. We are not using anything. In fact, I'm going to take these off because we're not using anything. I'm not even using my headphones. I'm not even using my hands, actually. We are just, no, I'm just kidding. I'm using my hands. But what we're going to do, hi everybody, we're going to build a convolutional neural network from just TensorFlow. And okay, so that's what we're going to do. And let me see who else is in here. We got Melcrafter and Simon. We got Daniel and Anthony. We got Look and Sambit and Arendu. Hard mode is on. Hard mode is on. Manuel. We have so many dope people here. Not audible. Am I not audible? You can't hear me? Is that the case? Because I'm going to just turn this off. You can hear me, right? Bonjour. Oh, we got an international crowd here. We got Ishan. We got Paolo. We got the whole world in here, guys. We have 200 countries represented in our community. That's amazing, isn't it? So what we're going to do is we're going to build this, and let's start off with a 5-minute Q&A. So just hit me with questions. I'm just going to go into it because I'm excited, and I hope you guys are. Okay? Hit me with your best questions. When is the Hangout for Patreons? It's going to be in 2 weeks. I'll schedule it soon. Thanks for the reminder. I know you from Daniel Oct1. Yes, I went to high school with him. He's a great guy. I'm doing great. Thank you. You're awesome too. Hi from the Netherlands and France and Italy and India. Oh my God, guys! We have just started this community, and we already have people doing amazing stuff. We had someone who gave a talk on R somewhere, I think in South Africa or something. We had someone who got their data set featured on the first page of Kaggle. So we have a lot of great stuff happening, and we're just getting started. So hello from Greece again. Why TensorFlow? Because TensorFlow is actually faster than NumPy. You heard me. TensorFlow is actually faster than NumPy. Why? Because it runs on a different interpreter than just Python. The Computation Graph has its own interpreter, and it can run in parallel. So it's parallel execution, and we'll talk about that during the talk. From Antarctica, only Eskimos here. We have Antarctica in the house. Where's the link to the OpenAI in GTA 5? I'll make a video on that within within a month. Please explain your hidden layer of this tutorial because in Pong Live you didn't explain. I will explain the hidden layers. I'm going to explain what's happening in each of the filter maps. Okay, 3 more minutes. Any application of ML in robotics? Sure, there's a lot. Control theories specifically, like ideal ways of moving your physical arm to pick up the object. And you can run a loss function, optimization function, use backpropagation, everything else, everything applies. It's just reinforcement learning. MNIST, exactly. We're going to use MNIST. The code is in the description. Google search bots, not yet. Best resources currently available for learning about generative modeling. Wow. I would say the best resources are for that Ian Goodfellow's book, because I mean he's the guy who made generative adversarial networks, and so if anybody knows about it, he does. And that's kind of that's still the bleeding edge. Any video coming up on Apache Spark and ML Live? Apache's like not that cool to me, but I mean if you send me a link, maybe I'll be convinced. CNN for speech, I have a few videos on that. Search TensorFlow speech recognizer, but I'll make more in the future. What is a good reference to learn about ML? My channel, watch all my videos. There's more content in my videos, and most people don't recognize this, than in the entire web. I have written essay after essay, week after week. My scripts for my videos are huge technical writing scripts across almost every topic at this point. And we're just gonna keep going, and there are more topics, and there's endless topics. 2 more questions, and then we're gonna get started. Resources for NLP. Let me talk slower. Resources, there's just so many questions coming in, guys. By the way, let me say that we have somebody from Udacity in the house. His name is Luke. So shout out to Luke, and he's going to be in here to help answer some questions because we got a lot of people here. So any questions you have, Luke is going to be answering. So Luke, if you're here, shout out so people can see you. All right. So 2 more questions. Kevin Murphy. Okay. Any image similarity detection in TF? There is. That's not what we're doing. We're not doing similarity detection right now, but it is possible in TF. And so there's Luke right there. Okay, so 1 more question, and then we're going to get started. How to practice ML in smartphone. How to practice ML in smartphone. Practice ML? You don't want to practice coding on a smartphone, but you can use ML on a smartphone by having a server with your neural net, and then you just call it with an API. Don't run your deep model on your mobile phone because it's not going to work yet. We need better, more robust models that run on less computation before we do that. Okay, so that's it for our questions. Let's get started with this. It's going to be awesome. We're going to run this code. The link to it is in the README. Okay, so let's start screen sharing and let's get started. All right. Here we go. My entire screen, all of it. Share all of it. Okay. So here we go. I say here we go a lot, so I'm getting better at certain things. I mean, I like saying here we go, but I'm saying less, and this is a function of having to do this wanting to do this every week. Okay, so here's our code. Okay, let me just play that out, and then let me get these comments over here so I can see them at the same time on my different screen. Okay, let me make this a little bigger because we are really going to dive into this. We're really going to go into this, like all the details. Okay, so okay. So here we go with this. Let me also just have my face in the corner because you gotta have the face. I mean, right? You just, not the screen recording, the movie recording. There I am. Whoa, too big, too much Siraj. There's never too much Siraj. There is for today, right now. Okay, so there we go, right there. And then the code goes here. Here we go. We're gonna build a convolutional neural network. CNN, this is fake news. Oh my God, please don't bring politics in here. I am politics free. I am politics free, okay? We are talking about AI. Don't bring that in here. Okay, so we're going to build a CNN. And why are we building a CNN? Why don't we just use OpenCV, right? Why don't we use OpenCV? It's easier, right? It's easier to understand. We can just talk about similarity because, right? Because CNNs outperform every other type of algorithm for image classification. They are the state of the art. The data set we're going to use for this is the MNIST data set, okay? We're going to use the MNIST data set, and it looks like this. And why are we using this data set? Because it is, Jan LeCun was the guy who first used it in his 1990, you remember the weekly video, he used it for his first convolutional net in the 90s, which worked really well, but now it works even better because we have more data and more computing power. The other thing is it's a great, easy to start with, multi-class classification problem. It's a multi-class classification problem, right? There are 10 classes here, one for every digit. One for every digit, right? So 1 would be 1, 2 would be 2, 3 would be 3. I know, Igor, it is a boring data set, but it's not about the data set right now. The interesting part is going to be this model architecture, and that's going to be the interesting part, okay? So 5 minutes to answer a question is not enough for 350 people waiting a whole week. Man, that is quite the pressure, but hey, it's all good because you know it's Gucci. It is Gucci. Okay, so here we go. So that's the MNIST data set. It's going to be a multi-class classification problem. And this is better than a linear model because the best we can get with OpenCV, is 91%. So we're going to use multi-class classification, and this is what it's going to look like. So let's start off by just looking at our architecture. Now this is a fully trained architecture that we are looking at right now. Man, you guys have the funniest comments. You guys have the funniest comments. I love you guys. Okay, so this is what a fully trained convolutional net looks like. And what we're going to do is we're going to look at this in detail before we get to the code. So let's just look at it. Let me blow this up a little bit. Okay, so here we go. We're going to start off with an input image, like 7, okay? We have an input image like 7. And we're going to put it into our convolutional net, and it's going to output a class. The class is going to be one of 10 different classes, okay? So that's what we're going to do. So how does it output that class is the question. What is the magic that is happening in a convolutional net to output a class? Well, it has layers. And so this is a trained network. So we're going to talk about a trained network, and then we're going to talk about how it became that good. So when we put an input image like 7 in, it's going to go to the first convolutional layer, like you see right here, this first convolutional layer. And in the first convolutional layer, we have 16 filter matrices. These are 16 5x5 filters. And filters can be thought of as weights, okay? They can be thought of as weights in a network. These are 16 5x5 filters. And what is going to happen with these filters is we're going to take this image and we're going to multiply each of the these filters by 1 pixel in the image. So it's going to go left to right. It's going to go from left to right. And what does this look like? Well, I have this very handy little animation here, which is also in the notes. And I need to remove the parentheses. But this is what it's going to look like. This is Andre's blog? It's somebody's blog. Where is it? Where is it? Where is it? There it is. This is what it's going to look like, right? It is convolving. The word convolutional. And I'm going to contrast it to other architectures in a second. Okay, well, hold on. But the word convolutional comes from convolving, because we are convolving from one part of the image across all of it. Convolving means sliding. We take our filter and we multiply it by, it's essentially a dot product. We are doing matrix multiplication. That's all it is. It's matrix multiplication. We're taking our filter and we are multiplying it by every part of the input image, and it's going to, and we're gonna, all of those, the results are gonna result in a feature map image. And now let's talk about what that feature map image looks like. Okay. So we're going to multiply each of these images by 1 pixel in the input image, and it's going to output 16 channels. And each of these channels is a matrix. And we can think of this whole thing as a feature map. That's what we call it. We call it a feature map. Or we could call it an activation map. Both words for it. And it's either a feature map or an activation map. There's 16 channels of this. And so that's the first image, right? We are multiplying one right from left to right, left to right, left to right, left to right. Let me show one more little animation of this. Let me show one more little animation of this. Hold on. There we go. So here's one more animation. And in this animation, right, and this was in the weekly video, it's sliding just like that, and it outputs the feature map. So we can think of this feature map as one big-ass image, right? Actually, there's several images, and it makes one big-ass feature map. So that's the word I'm trying. So there's several images, okay? This is going to be uploaded to YouTube right when I'm done. But it's better to watch live, exactly. So that's what's going to happen. So, okay, so that's what's happening in the first layer. It's going to create a bunch of images. Guys, be nice to each other. We're going to create a bunch of images, and then in the next layer, it's a little more complicated. In the next layer, it's a little more complicated because we have a 16 by 36 set of filters. So there's 6. We don't actually see all of them here. We only have this first 16 set, the second 16 set. Dev Patel will probably play me in a movie one day for sure. I'm sure about it. But somebody will for sure. I'm convinced there's going to be a movie about me one day. So we're going to have a 16 by 36 convolutional layer. And each of these is, we're going to multiply by each of these. So for the first, so here's what's going to happen. So for this first image right up here where my mouse is pointed at, let me blow this up a little bit. Let me make this a little bigger. This actually didn't make it bigger. It just made everything but this bigger. So good job, Mac. Good job, MacBook. Hold on. So we're going to multiply each of these images by each of these pixels in one image. And we're going to, so all of these, and we're going to sum them all up. So let's talk about this first left corner pixel at the top left. We're going to multiply every single weight up here, all 16 of them, by that 1 pixel, and we're going to sum them all together. And the sum of that makes up a single pixel right here. Then we're going to take the next 16 and multiply it by the second pixel. And then the next 16 and the next. So we're going to take, so basically all of these feature weights, all of these filter weights are multiplied and summed together to make a single image right here on this new feature map that's even bigger. And we're going to do that for every single image here. So what happens is these channels, these 36 channels, it's a bigger feature map and they're more dense. And what do I mean by more dense? It's only focused on the features that it thinks are relevant, because all of the features it thinks are relevant are going to show up here. Then, okay, so once we have that, so you have 16 filters, yes. So we start off with 16 filters, and then we start off with 16 filters, and then we get 16 by 36 filters. And these are 5 by 5 pixels, and it's just a matrix of numbers. It's a matrix of numbers, okay? Rohan Pinto, okay? So So it's a matrix of numbers, and then we take our fully connected layer right here, our fully connected layer, and so what our fully connected layer does is it takes that huge multi-dimensional feature map and it squashes it into a two-dimensional feature map. It squashes it into a two-dimensional feature map just so we could then squash it with a sigmoid in the output layer. And what happens when we squash it with a sigmoid is it's going to give us one of these 10 different probabilities. And one of these 10 different probabilities, we could then convert to a class, which is going to be 7. Okay, that's the very highest level that we're going to talk about right here. Okay, so that's the very highest level, and we're going to talk about it in detail as we write the code. As we write the code, we're going to talk about it in detail. Now, one interesting thing about convolutional nets that I really like is we can understand how they work, but we don't understand so well. We can understand perfectly how they work, all the matrix multiplications. We can get from a high level why these series of abstractions can detect a feature or how they can detect a feature, but we don't know why it works so well. And that to me is very exciting. And we'll talk about that in a second. So that's the highest level. So let's keep going now. Now we're going to get to start building this thing, okay? Before we start, let's just talk about this is just another example of convolution that's happening in the first filter. This is one more example. So the red, so here's the thing about this. So this is why it's red and black. So the red filter weights means that the filter has a positive reaction to the black pixels, while the blue filters means the filter has a negative reaction to the black pixels. And why? And why do I mean by positive and negative? Positive means that it has detected something, that there is something there, and blue means that there is nothing there. And so what happens is it's only going to get what it considers to be relevant. And this is what it considers to be relevant in the first feature map. Just this line over here. This feature, it considers to be the relevant feature in the first feature map, okay? That's the result of the first convolution. And it does this for several. It's going to make several of these images. They're all going to look like each other, but for different parts of the number. They're all going to look like the number 7, but it's going to highlight different parts of it, okay? Sankit, yes, I did explain in the next video. Thanks for calling that out. But okay. So that's what's going to happen. So now let's start writing our code. We'll start off by importing our dependencies. We got Tensorflow and NumPy, scikit-learn, and we'll talk about each of these when we get to it. How does it determine what is relevant? That is the question. That is the question. We don't know why it determines these certain features as relevant. What we do know is it can detect what is relevant. We know how it detects relevancy by multiplying matrices together and then outputting a binary yes or no, as in the feature is there or the feature is not. But we don't know why. Why it's determining that this specific thing is relevant. So that's really interesting, right? So let's get started with this. Basically magic. No, I mean, we're going to figure this out. I mean, give it like a few months. I'm sure someone's going to output a paper on this. So let's start building this. Now, we're going to start out by defining our hyperparameters. Our hyperparameters, in this case, are going to be the convolutional layers. Why do we define a 5 by 5 filter size for this feature map? Now, somebody asked me why I didn't do a, can I explain the difference between architecture? So let's talk about a fully connected layer for a second. Let's talk about a fully connected layer, okay? So if you look at this image, see this image? It's showing a box, and this box represents a 3D filter. It's representing a 3D filter, a three-dimensional filter. And the third dimension, by the way, is the depth, which is RGB values. So it has 3 different two-dimensional matrices, one for red, one for green, one for blue. And the reason we're not using a normal feed-forward neural network with a fully connected layer is because there would be a combinatorial explosion if we multiplied a 3-dimensional input image by a 2-dimensional set of weights. It would be a huge number, okay? Especially for big images with 1080 pixels. So that's why we use a convolutional layer instead of a fully connected layer. That's why we use that, because it is a smaller, it gives us a smaller result. So back to where we were going. So that's why we're creating our filter maps. And it's 3D because there are 3 color channels: red, green, and blue. Red, green, and blue. Okay, so we define our filter size as 5 by 5. So that's going to be a specific size for all of those little filters that we saw up there. It's going to be a 5 by 5 quadrant. Okay, thanks, Sarah. So, and then we're going to find a number of filters. There's going to be 16. And so that's going to be in our first filter. There's going to be 16 of them. And then for our first layer, it's going to be 16. For our next one, there's going to be 36. And I'll explain why we use a fully connected layer at the end, because we do use a fully connected layer at the end. And we'll define it as a size to be 128 here. So those are our hyperparameters for our layers. And then we load our data set. Our data set is going to be the MNIST data set. We set one hot to true, which means we're going to use one hot encoding. One hot encoding is an encoding scheme that is very simple, that it converts them to binary ones or zeros, which is great for a simple classification, which is what we're about to do. So this is our data. It's going to be stored in the data initialization. Why these numbers? Well, we could try. So choosing hyperparameters is its own field of study. Should we do big hyperparameters, small hyperparameters? Usually we test out different things through guess and check. There are actually hyperparameter optimization methods, search strategies for our neural net to try out different sets of thanks, Luke, for answering that. Try out different sets of weights, of hyperparameters. So that's for our loading data. And so we're going to load up our training, test, and validation data right now. Okay? And then we're going to define some more hyperparameters. So we know that those MNIST images are 28 pixels by each dimension. So we'll define it by image size. These are we don't want to have what's the computer science word for it? We don't want to have not magic numbers, but I think it's magic numbers, right? We don't want to have magic numbers. Those are just scattered values in our code that we don't want to think about, right? So that's why we're going to define these features, define these variables beforehand. Then we're going to define our image size as flat. So it's going to be a one-dimensional array of this length. And then our tuple. And so it's a tuple because we're going to input a tuple into the, this is our input. We have our image size, and then we're going to define the number of channels. There's going to be one because we're using grayscale. Luckily for us, this, so I talked about 3D convolution when we have an RGB, when we're using RGB. But in this specific case, this is grayscale. These are grayscale MNIST numbers. So then we're only going to define one channel. But if we're using color images, we define how many channels? We're going to use 3 channels. Yes, I'm doing a time series video on Friday. It's going to be dope. You guys are going to love it. It's going to be really popular. Then we're defining the number of classes, 10 of them. Okay, because there are 10 numbers. Now let's plot out these images. This is a simple NumPy plotting code to plot out the number of images. Okay, this network can be used for CFAR with some modifications that I'll talk about at the end. So when we plot out these images, this is what it looks like. It's going to it's not predicting anything here. It's just plotting out the images and their labels. Okay, images and their labels. Oh my God, time series is going to be so amazing with LSTM networks. I'm going to talk about it on Friday. So that's it. So now let's talk about TensorFlow. Now I talked about how TensorFlow is scalable. It's scalable because it can be used on CPUs and GPUs. If you run it in the cloud, you can easily scale it across GPUs, and you can define how many GPUs you want to run it on. You cannot do that with just NumPy. That's why it's better than using just NumPy. Any kind of production-grade machine learning that you want to do not do it with just NumPy. Use TensorFlow because it is the best machine learning library that we have so far. So the first thing we're going to do before we start defining our computation graph is we're going to define helper functions for our weights and our biases. Our weights are going to be initialized randomly. They're going to be initialized randomly, and we are just defining variables for them. We're not doing anything else. We're just defining variables. And then our biases. Why are we using biases? What is the point of biases? So explanations for use of biases are actually really bad across the net. We can think of biases as, we can think of them very intuitively for linear regression models because we just think of them as the y, we think of them as the y-intercept in a y equals mx plus b slope formula. It's just a y-intercept. But for a multi-dimensional array, or sorry, for multi-dimensional computation, such as the case in TensorFlow, we use biases as a constant value to across. It's always going to be a constant value, and it's carried across the matrix map. And what this does is it improves convergence. It makes sure that our our model is more accurate by having a constant value, a kind of anchor point to where we started off and between where we started off and where we ended. And we'll talk about biases more. Okay. They make it, yeah, to the highest level. It makes it easier for the math to optimize. So those are our two helper functions. We haven't actually started building our computation graph yet, right? Okay, we didn't start building our computation graph, didn't do the math. It's gonna be all right. You can sit back and laugh, but it's okay because we're gonna go so hard, you're gonna barf in this class. I rhymed all that, by the way. So this is our convolutional layer. In our convolutional layer, we're going to define our previous layer, then our input channels, our filter size, the number of filters, and then use pooling to 2. Let's talk about pooling. I did not talk about pooling. So before we look at this, let's go back to the image for a second, and let's talk about 2 more things that we didn't talk about. Let's go all the way back up to this initial image that I showed you guys. So in the first convolutional layer and the second convolutional layer, it's not just convolving. It's performing 2 other operations. It's performing pooling, and it's performing ReLU. Now we perform ReLU to increase the nonlinearity of our model. That makes it easier for our model to learn nonlinear functions, which is the case for this. It turns all of our negative values into zeros, okay, and then which improves the nonlinearity, and we'll talk about that when we do that in a second. But then we're also doing max pooling. Where pooling is an operation where we just take the best parts of what we just calculated. And by best, the max values, which is those, it's kind of like convolving, where for every part of the matrix, we're just saying, what is the max value from this matrix? So if there's like 6, 7, 8, 9, we'll take 9. And there's an entire field of research over pooling, and we'll talk about that later on. But it's taking the max value. So back to where we were. I just wanted to define those 2 processes that we're doing. Okay? So back to this, the convolutional layer. We're going to have a shape, and the shape is going to consist of all of those parameters that we define. What is the size of our filters, the number of input channels, which is 1, because this is a grayscale image. Okay? And the number of filters. Biases and our weights, now that we've actually created helper functions, and this is the actual initialization step, right? Well, for a convolutional layer. So our convolutional layer is actually a block, and it consists of 3 operations. Remember, a convolutional layer isn't just a series of matrix multiplications and a summation of all those. It's also a right, it's also ReLU, and it's also what else is it besides ReLU? It's also using pooling. So there are 3 operations that are happening in a convolutional layer. Okay, 3 operations. And so this is the default TensorFlow. This is the default TensorFlow convolutional 2D function, okay? And we're wrapping this in our own function so that we can add biases, and we can add, we can use biases, and we can use weights. Now, here's another thing. Now, in this convolutional layer, we know about our input, we know about our weights. What are strides? Strides are, think of striding like in real life, right? What is a stride, by the way? Like a stride is when you you take a big stride, you take a big ass step, you take a big step. And that's what striding is in a net. It defines how, what are the intervals that we are creating these multiplications, right? So is it every pixel? Is it every 2 pixels? Is it every 3 pixels? That's what we define as strides. So the smaller the stride, the more accurate it's going to be, but it's more computation. So there's a trade-off. More accurate classification, but more computation. Then we're defining padding. It's a massive big step. And then we're going to define padding. So padding is going to be same, which means the input image is padded with zeros, so the size of the output is the same. Okay, so that means that the difference between the input image and the filters, the matrices aren't the same size. So we'll pad it. So we'll pad the smaller one with zeros, so they're the same size. We want them to be the same size, so it's easier to perform matrix multiplication, and so the output is going to be the same. That's why we perform padding. Then we're going to perform pooling, and so downsampling is what we call this process of pooling. Downsampling is the name of this process. We call all sorts of pooling, max pooling, average pooling, all sorts of pooling. We call it downsampling. And TensorFlow has a built-in function for this called max pooling, where we define the size of the pool and then the strides as well for the pooling. So it's similar to convolution. It's similar. It's a similar process. It's a kind of like a flashlight that's shining over the image. And the part that it's looking at, remember, is called the receptive field. Whatever it's focused on is the receptive field. Okay, so then we'll define our, so then our third operation, and this is the third operation in every convolutional block, is going to be rectified linear unit, or ReLU, which is going to calculate the max value, which turns all the negative numbers to zeros. It's similar to absolute value, and it allows it to learn more complicated functions than just linear regression. Those are the 3 operations that occur in a convolutional block. In a traditional CNN, 3 blocks are there, right? This happens 3 times, and then we squash it, and it outputs a probability. This is going to return our layer, which is what the resulting layer and the resulting weights after we perform these 3 computations on it. Okay? Now, we're going to do that 3 times, and then we're going to flatten the layer. We're going to flatten it using a fully connected layer. So, okay, so let me just talk about the steps here to flatten the layer. To flatten the layer, let me have some coffee for a second. To flatten the layer, we're going to first take the layer shape. Okay, what is the shape of that layer? What is the dimensions that it's going by? And then we're going to say, how many features does this layer have? Okay, what are the features? And to get that, we're going to use the num_elements function. We're going to use those features, and those features are what we want to squash. And the word squash means reduce the dimensionality. Okay, we want to reduce the dimensionality to a 2-dimensional vector, which we can then reduce even further into a scalar, and that scalar, which is a single value, is going to be our probability. It's going to be our probability. I am made up of a drive to solve intelligence because I have traveled and I have seen all the problems in the world, and it is the most important thing in the entire world. I will die for this cause. I will die for this cause. So layer flat is that last shape. Once we reshape that number of features, layer flat is going to be that 2-dimensional vector, okay? And then we were going to return that, okay? So then for our fully connected layer, we're going to perform matrix multiplication and then focus. All right. So hold on a second. Once we flatten the layer, we input it into the fully connected layer as a dimension. And it's going to output the fully connected layer a probability. That's what it's output. It's going to output a fully connected layer, which is a probability. Okay, so all we did so far was we defined our helper functions. Now let's build our graph using these helper functions. And because we defined all of these complicated helper functions, now we can easily define our computation graph. So we start off with our placeholder value. The placeholder is going to take in that image, right? The image is going to be a 2-dimensional grayscale image, right? It's going to be a number. So it's going to be not just the image, we're also going to input the label. So we have two placeholders for the image and the label. Then we're going to input it into our convolutional layer. Yeah, I'm gonna do a Q&A session after this to explain things more. Okay, so write down your questions. Okay. All right. So then let me remove me so I can. Okay. So that's gonna be that. So let's define our first convolutional layer. Let's define our first convolutional layer using our helper function that we created. Our first convolutional layer is going to take the image as an input and create a set of filters, and each of those filters has a width and a height equal to the filter size that we define. And then finally, when we wish to downsample it using max pooling, so it's going to be half the size, that's going to be our output. It's going to be that feature map. That's going to be our first filter, and we can look at what happened here, right? It's a TensorFlow object, tf.tensor. We define ReLU on it, and it's going to be a shape of size (1414 by 16), and then the type is going to be float32. This is a matrix of values, right? A matrix is a table of values, of pixel values. We'll do that again for the next convolutional layer, right? So there are two convolutional layers. We took the output of that first layer and we fed it into this next layer. Then we're going to flatten it. We're going to flatten it. We're going to flatten it using the we're going to flatten it over here, right? It's a 4-dimensional tensor. I'm going to flatten it into a 2-dimensional tensor using that helper function we created, right? So if we were to then visualize that flattened layer, it would be, the shape is going to be 2 dimensions, right? For the first time it had four numbers here, right? Because it was 4 dimensions, and now it's just 2 dimensions, okay? So now we're going to look at the number of features, which we have a lot of features, and so now it's time to flatten that flattened 2-dimensional vector into a probability. And we're going to do this twice. So we have 2 fully connected layers, okay? We have 2 fully connected layers here. And for each of them, we're going to define them. We already defined the helper function. So what we're going to do is we're going to run them both on that input data, and it's going to output this 2-dimensional vector, which we can then squash using a softmax function. Okay, the softmax function is a sigmoid function. It's going to output a probability, 1 of 10 classes. This probability is going to be mapped to 1 of 10 classes. And the way it's going to be mapped, the way our network knows where to map this, is by using an optimizer and a loss function. Okay, so this is the gradient descent and optimization step. Okay, so for our gradient descent and optimization step, we're going to use, okay, what is that? What is our loss function? It's going to be called cross entropy. Cross entropy is our loss function. Here's a great Quora link for the cross entropy function, like learning about it. So basically, it's similar to softmax, except instead of in a softmax function, we're determining the type of activation layer. But in cross entropy, we're using it to measure the error at the softmax layer. It's similar to softmax, but different because we're using it to measure the error at the softmax layer. So it's a loss function because it's going to output an error value, and we're going to use this error value that it's outputting, right? Between the real and expected value. So it's going to output a prediction, right? It's going to be like 60% chance that it's a 0.70, but in reality it's a 100% chance that the number is. There's a 60% chance that the number is 7, but in reality it's a 100% chance that the number is 7. So that difference between the 60% prediction and the 100% reality, that error value is what we want to minimize. And the way we minimize that error is using an optimization method. Now, ATOM is just another word for gradient descent. It's a type of gradient descent optimization function. Now, gradient descent determines the direction that we want to update our weights. Our weights in this case are going to be those filter values. How do we update those filter values so they are more accurate, that they give us a more accurate result, that they are more closely aligned to features that would be in the image. How can we modify those initial matrices in those filters such that they output a more accurate prediction? Now, gradient descent is going to give us that because it is using the chain rule. Because okay, so gradient descent. I mean, that could be a whole explanation. So let's talk about it. Let's talk about gradient descent a little bit. So for gradient descent, we're using the chain rule. So what is the chain rule? We're taking the derivative of the loss function, and we are recursively taking the derivative of each layer, back propagating our loss to each layer. And then we're updating our weights using the gradient. So I've explained this a couple times in a couple videos, but honestly, I need a video just for back propagation, and that's going to come up very soon. But it is back propagating weights by taking the derivative recursively across each layer. Okay, and there's probably a great image for this. Back propagation, recursive derivative. It's all about recursion when it comes to back propagation. I mean, the chain rule is just recursively taking derivative of derivative of derivative, and that's from statistics. So knowing the chain rule is very important. You have to know how back propagation works because it is the optimization method that is used across neural networks. And so with TensorFlow, we can basically just plug and play. It's a plug and play model to just type in whatever type of optimization function we want to use, and then it's going to minimize that loss over time. Okay, so then we'll use the reduce mean. So then we're going to use TensorFlow's reduce mean function to measure the classification accuracy. Okay, so it's a binary yes or no value, 0 or 1, true or false. Okay, so then we're going to run our session. Right? We always have to run our computation graph once we built it. So then, so once we run our session, so this is us running our session, and then we're going to plot our values after a set of iterations. Okay, we have to a set of iterations. These are all just printing out testing the accuracies and training accuracies. But really, what I want to get to is we've created our graph, we've run it, and now we want to see the accuracy. So after one run, so after a small set of batches, we have a 13.7% accuracy, which is very terrible. It is worse than linear regression. It is terrible. We never want a 13.7% accuracy, right? But after training it even more, one optimization iteration, we have a 14.3%, right? So after 100, we have 59.8%. So you see that the more we run this optimization, the more accurate we get. After 1,000, we have 90%. Okay, and so 1,000 would take probably on a standard grade 2015 MacBook with a probably a 2.7 gigahertz CPU. 1,000 iterations of this would take like 30 minutes or less. Okay, so this is all computationally possible on a local machine right now. We don't have to use the cloud for this stuff. Okay, this is multi-class classification. That's what this is considered, multi-class classification. So let's visualize those weights that we created, right? So this is using Matplotlib to visualize those weights, okay, because those are matrices. So we're going to visualize those matrices using Matplotlib. And if we look at those weights that we just visualized, so let's look at those visuals. Okay, this is an image from the test set. These aren't the actual visual lists. These are the visualizations. So we've colored the relevant parts of the matrix red and the irrelevant blue. Okay, binary, right? So why is it that this line is what's considered to be a good feature? Or why is it that it's considered this bottom right part to be a good feature? We don't know why. But what happens is it's going to be more and more accurate. These features are going to be more and more close to what we want to make the accurate prediction. So that's what it looks like. It's a matrix of pixel values that it learns at these weights, these filters, right, between each of the convolutional layers. And so if we plot these, what's happening in these, this is the feature map. This is what it looks like. And see, it's highlighting different parts of the image. It's going to combine all of these to output a probability. Okay? And so in the next convolutional layer, we have even more filters. We have 16 by 36, even more features. And those are the results. And then we close the session, right? Always close it when we're done. Okay, and then there are more exercises. So yeah, that's it for our convolutional layer. And let's guys, stick around for a second. Stick around. Let me go back to stop screen sharing. Okay, so go ahead and ask questions, guys, because we have some questions to ask. Okay. The notebook is in the description. I'm going to add the README in a second. I am so proud of all of you guys for being in this live session, for watching this video. It is awesome to see you guys here. This stuff is not easy. It's not easy, but it's very important. And knowing this is going to put you a huge step above everybody, every other developer. Just the fact that you even recognize little things about convolutional nets is very important, okay? For your career, for your academic career, for any startup that you want to do, it's very important because all successful startups, all successful companies, all successful academic research in computer science that's going to be at the bleeding edge, that's going to get the most attention, is going to involve deep learning at this point. And then we're going to build on that later, and it's going to get even better. So I'm very proud of you guys for being here, okay? You guys are awesome. I am honored to be a part of this community. Okay, so the room is soundproofed, and next week I'm going to actually improve the quality of this live stream, so I'm very excited for that. Okay? We are growing so fast. We have 500 developers joining this community every single day on average. We are growing so fast. So it's a very exciting time to be here. And I'm just going to get better at explaining, and you guys are just going to get better at doing these things. I mean, it is just incredible the amount of coding challenges you guys have done. It is incredible what you guys have done. It is just incredible. So, okay, can I share resources to help you grok CNN? I'm going to put so many CNN resources in the description, it's not even going to be funny, within the hour. If you want the image to be manipulated, do I add another matrix to affect the color channels? Have it output multi-channel image. The image to be manipulated, if you want the image to be manipulated, we're going to perform an entirely different optimization process, not gradient descent, but gradient ascent. And that's what's used in neural style transfer. And we're going to get to that 3 videos from now. Have you heard about Good AI challenge? No. Can this be done with Python with same level of difficulty? Python, this was Python. Okay, guys, can you do more stuff on financial subject? Yes, it's coming out on Friday. Is max pooling done across channels or a specific feature frame? Max pooling is done across all channels. It's every Wednesday at 10 a.m. PST. Also tune into the next live stream because it's going to be even better quality. I'm not going to use Google Hangouts. It's going to be even better quality. Okay, thanks, Koshikara. We have so much to do. We have so much to do, guys. Remember to share your victories with all of us. One victory is a victory for all of us. You are a very special person for knowing neural networks. You don't even understand how important you are to the future of the human race. Even every commit counts on GitHub. Every commit to every repo counts because it's like the butterfly effect. You guys know the butterfly effect? If a butterfly flaps its wings in Colombia, it's going to cause a tornado later on somewhere in a different continent. It's like that for code in machine learning. The rate of discovery that is happening. The fact that you even push any open source code to GitHub is going to be even looked at by any other developer. It's very important because then they're going to build and they're going to build and they're going to build and other people are going to build. So it's all connected. Everything we're doing is connected here. Okay, so don't think that anything you do is meaningless in this field. Everything that you open source, everything that you output is going to have immense value to the entire world as machine learning propagates across every industry, okay? So let's cause tornadoes with code. Let me answer 2 more questions and then we're done with this live stream, okay? Can you make a video on GAN? I have a video on GAN. Search generative adversarial networks. I'm gonna do another one, it's gonna be even better. Any Slack group or place where we can all discuss? Yes, I have a Slack channel. It's in the description of every single video of mine. Join the Slack channel, okay? There's a lot of great people in there. Okay, so that was one question. One more question. How do I learn besides constant practice? How do I learn? I input a diverse set of sources. So I have, if I'm learning about convolutional LETs, so like for this past video, for example, I had Andrei Karpathy's the unreasonable effectiveness of neural networks epic blog post up in one tab, and then I had another tab from, I think, Chris Olah, great blog, by the way. Chris Olah, Andre Karpathy, two of my favorites blogs. And then I had, you know, other tabs. And so what I'm doing is I'm going between different tabs, and I'm max pooling. I'm taking the optimal information from each of these, and I'm saying every time I have a question, one, let's look at another source. So you have to have multiple diverse sets of learning resources, okay? So that's how I learn, and I truly love what I'm doing. So I think it's very important to love what you're learning, because that is such an important thing. And I believe in myself. I believe in myself. That's such an important thing. And you guys all need to believe in yourselves as well, because you are very, very important, okay? You guys are awesome. I'm so honored. I'm so honored to be here every Wednesday making videos for you guys. And the community is getting better as well. Our community is getting better. People are helping each other in the comments. The number of coding submissions are going up every week, and the quality of the coding submissions are going up every week as well. So we are all getting better. It's incredible. And we are a force to be reckoned with, guys. We are a force to be reckoned with. Okay, so that's it for our questions. And so now I'm going to end it with a motivational rap. Okay, so any guys, and by the way, there's so much money to be made here, and we're going to talk about all the money to be made as well from each of us. Okay, we are all going to get very rich. Not that that should be the driving factor. That is a good thing. It's good to build wealth. The driving factor should be to make as much of an impact as you can, and as a side result, you will make money, because this stuff, I'll make a video on that, like ways to make money with machine learning. I know it's going to be important. So freestyle. Okay, D3.js, that's my freestyle, D3.js, okay. Hey, yo, when I visualize matrices, I use D3. I do it with JavaScript. Can't you see? I see all these matrices in a vector. It's like 3D. It's like 2D, 1D, scalar, vector, tensor, all these words, man. I don't know. Call me Victor. I was looking at all these statistics. I was looking at linear algebra with sticks. I was hitting it with my brain every day. I went back, yo, it's gonna be okay. Okay, so that was it. Everybody's gonna get rich. Okay, what's the name of the Slack channel? It's called Programming Wizards. That's it for the video. Thanks for being here, guys. For now, I've got to make the sickest stock prediction video using LSTM networks. So thanks for watching.